Imagine this, a multi-million-dollar autonomous rover up on Mars.
Oh, massive stakes.
Exactly. Like, it has flawlessly navigated the vacuum of space. It survived this insane fiery atmospheric entry and safely touched down on the dirt.
It's a huge engineering miracle just to get there.
Right. And so the engineers at Mission Control, they send a really basic command. They say, drive 100 meters straight ahead.
Just a straight line?
A straight line.
Yeah.
And the rover's motors, they spin perfectly. Its internal math is totally flawless. But then a week later, the satellite imagery comes back, and they realize the rover didn't drive straight at all.
Oh, no.
It drove in this massive sweeping arc and literally hurled itself off the edge of a crater.
Just completely destroyed.
Completely. And the reason, the physical rubber on the left wheel was like a single millimeter thicker than the right wheel.
Wow, 1 millimeter.
1 millimeter manufacturing variance, right? Compounded over thousands and thousands of rotations, and it destroyed a billion-dollar mission.
Yeah, I mean, that is the ultimate stakes of robotics right there.
Yeah.
It's this constant, brutal war between perfect internal mathematics and the completely flawed, unpredictable physical universe.
Exactly. And for you, the listener sitting right there, the stakes are actually incredibly personal right now.
Oh, yeah, we know your mission.
We know exactly why you're here. You are staring down the APJ Abdul Kalam Technological University's 6th semester exam.
Course code AIT 304, Robotics and Intelligent Systems.
And your goal isn't just to, like, scrape by and barely pass. Your goal is to become an absolute god at this material.
Right, to understand the underlying physics and logic so deeply that the end semester examination feels like, I don't know, child's play.
We're going to make you remember everything. We're going to make you ace this exam.
Absolutely.
So we are going to engineer this entire deep dive around the AIT 304 syllabus and the exact model question paper that KTU provided.
But we are totally abandoning the textbook approach.
Yeah, reading a syllabus chronologically is just a great way to fall asleep.
It really is.
Instead, we're going to literally build a robot from scratch together.
I love this approach.
Right. We'll start with this inert metal and wires, give it senses, teach its brain the linear algebra of 3D space.
Then force it to map an unknown room.
Exactly. And finally, inject artificial intelligence so it can navigate totally autonomously.
So the battlefield you are walking into, it's a 3-hour exam worth 100 marks.
Big test.
Yeah. And the critical intelligence to keep in mind here is that 40% of your continuous assessment and the final exam, it's heavily weighted towards the apply category of Bloom's taxonomy.
Right, the apply category. But what does that actually mean for the test taker?
Well, it means the examiners, they do not care if you can just regurgitate a dictionary definition of a wheel.
Anybody can memorize that.
Exactly. They will give you a specific mathematical environment, a defined coordinate frame, or like a physical payload right there on the paper.
And they'll demand that you apply kinematic formulas to solve the state space.
Right. Understanding the why and the how is literally the only key to unlocking those massive 14-mark Part B questions.
Okay, so let's get into it. We begin with a pile of metal. Module 1.
The physical body.
To stop our rover from driving off a cliff, it first needs that physical structure. Every single robotic manipulator, from a factory welding arm to a tiny surgical micro-robot, is constructed from 5 fundamental components.
Right. Links, joints, actuators, sensors, and controllers.
And the engineering paradigm here, it actually maps perfectly to human anatomy, just with, rigid mathematical constraints.
Yeah, the human arm provides an excellent heuristic for this.
Yeah.
Like your bones, the humerus, the radius, the ulna, those are the
That's
links.
structural pieces.
Exactly. And in robotics, these are modeled as perfectly rigid bodies. We assume zero deformation under load, which really simplifies the kinematics.
So the metal doesn't bend in the math.
Right, exactly. Then your elbow and your wrist, those are the joints. They constrain the relative motion between those rigid lengths.
Makes sense.
Your muscles are the actuators, generating the torque. Your peripheral nervous system provides the sensors, feeding back state data to the brain.
Feeling where your arm is.
Yeah. And your motor cortex is the controller, calculating the inverse kinematics required to, say, place your hand perfectly around a coffee cup.
That biological intuition is so helpful. Let's translate that into the pure math of degrees of freedom, or DOF.
Oh, this is a big one.
It is. The KTU model paper hits this immediately with question 1 for 3 marks. It asks, what do you mean by degrees of freedom?
Classic question.
And then it asks, how many degrees of freedom are required for a drone to achieve any position in 3D space? And how many more DOF are required for achieving any orientation as well?
So if we are aiming for maximum marks here, we can't just say the ways it can move.
Right. That's too simple.
Way too simple. We need to define this in terms of independent variables. The engineering standard definition is the minimum number of independent parameters required to completely specify the configuration of a mechanical system in space.
Minimum number of independent parameters. Got it.
Yeah. So for the drone, we look at the special Euclidean group, SE3.
Okay, SE3.
To place the drone's center of mass at any specific arbitrary position in a room, you need an X, a Y, and a Z coordinate.
Forward, backward, left, right, up, down.
Exactly. That is pure translation. 3 degrees of freedom.
But just pinning the center of mass in the air, that doesn't mean the drone is actually stable, right? Like, it could be pointing straight down at the floor or tilted totally sideways.
Which is exactly why we introduce orientation. To specify the drone's orientation around that center of mass, we need 3 independent rotational parameters about those X, Y, and Z axes.
Like roll, pitch, and yaw in an airplane.
Precisely. So 3 independent variables for translation plus 3 independent variables for rotation yields a total of 6 degrees of freedom required for unconstrained operation in 3D space.
Boom. 3 marks, totally secured.
Easy.
Now, the silliest throws this whole alphabet soup of robot arm configurations at us, like PPP, RPP, RRP, RRR.
Yeah, the P and R stand for specific joint types.
Let's break that joint mechanics down. So P stands for a prismatic joint, and R stands for a revolute joint.
Right.
A revolute joint is pretty easy to visualize. It's just a hinge. It rotates around a single axis, like your elbow.
Yeah, it revolves.
But a prismatic joint, that slides along a single linear axis.
Think of a hydraulic piston or the sliding rail of a 3D printer head. A prismatic joint translates while a revolute joint rotates.
Okay, so when the exam asks about a PPT configuration, 3 prismatic joints right in sequence, it's basically asking you to visualize the reachable workspace.
Right. What can it physically reach?
If you have an arm that can only slide left, right, forward, back, and up, down, the outer boundary of every single point that arm can reach forms a rectangular prism.
It operates in pure Cartesian coordinates.
Right, a giant 3D box of reachable space.
Like an overhead gantry crane in a shipping yard. That is a massive PPP robot.
Oh, that's a great example. So contrast that with an RRR configuration. That's an articulated arm with 3 rotational hinges.
Yeah, completely different math.
It doesn't move in straight lines natively at all. It sweeps through arcs and angles.
Yeah, its maximum reach forms this complex, spherical, or like teardrop-shaped workspace.
You'd have to use some really heavy trigonometry just to make the tip of an RRR move in a perfectly straight line.
Oh, absolutely. The inverse kinematics for that are intense.
Okay, so moving from stationary arms to mobile bases, the syllabus introduces wheeled, legged, aerial, underwater, and surface water robots.
Right, the whole fleet.
And the apply aspect here focuses on the dynamic characteristics. So speed of motion, load carrying capacity, and speed of response.
And it's crucial to understand these are not independent variables. They are fiercely competing constraints.
Like a trade-off. Let's look at the physics of that. If you want a robot with a massive load carrying capacity, say a robotic forklift, you have to gear down the motors heavily to generate immense torque.
Yeah, you are fighting inertia.
Exactly. You literally cannot have high speed of motion when you were moving a 2-ton payload because the kinetic energy would be catastrophic if you suddenly needed to stop.
It would smash right through a wall.
Right.
And then there's the speed of response, which is how quickly the system can react to a control input without becoming unstable. That is deeply tied to the mass of the links and the payload.
Give me an example of that.
Okay, think of a lightweight surgical robot arm. It has an incredibly high speed of response. It can reverse direction in milliseconds to avoid hitting a nerve.
Because it weighs almost nothing.
Exactly. Its load capacity is measured in grams. The exam will definitely test your ability to weigh these dynamic characteristics against specific use cases.
Awesome. Okay, so we also need to attach a tool to the end of this arm, the end effector, basically the hand.
Right.
We have mechanical grippers, magnetic, vacuum, and adhesive. But I want to really drill down into a very specific course outcome, CO1.
Oh, active versus passive grippers.
Yes, it demands we differentiate between active and passive grippers. What is the fundamental difference in the energy state of the system here?
So the distinction lies entirely in the origin of the actuation energy. An active gripper relies on an external power source that is dynamically controlled by the robot's central processor to initiate and maintain the grip.
So it's actively using energy to hold on.
Exactly. It requires a continuous flow of electricity to a motor or continuous pressurized air to a pneumatic cylinder to force those mechanical fingers closed against an object.
Got it.
If you sever the power cable to an active gripper, it drops the payload immediately.
But a passive gripper is different. It harvests energy from the environment or from the actual kinematic motion of the robot itself.
Yes, a passive gripper does not have internal motors or pneumatic lines.
Wait, then how does it grip?
It might use a spring-loaded toggle mechanism. So the robot arm physically rams the passive gripper against the payload, and that kinetic impact forces a spring past a mechanical dead center, locking the fingers closed.
Oh, wow, like a trap snapping shut.
Exactly. And to release it, the robot just presses a little release pin against a hard surface in the environment. It requires zero electrical power to maintain the grip because it utilizes mechanical bistability instead.
That is a phenomenal engineering distinction for the exam. Active requires control power to grip. Passive utilizes external kinetic force and mechanical geometry.
It's a very elegant solution when you need to save power.
Absolutely. Now, before we leave the physical body, the syllabus mandates a review of Isaac Asimov's 3 laws of robotics.
Yeah, a bit of history and ethics.
They originate in science fiction, but they represent the philosophical boundary conditions of autonomous operation.
So, first law. A robot may not injure a human being or, through inaction, allow a human being to come to harm.
Pretty fundamental.
Second law. A robot must obey the orders given it by human beings except where such orders would conflict with the first law.
Right.
And the third law. A robot must protect its own existence as long as such protection does not conflict with the first or second law.
Right. They lay the groundwork for modern AI safety and deterministic constraints. It's a highly probable 3-mark Part A question, so commit that hierarchy to memory. Okay, so we have a fully assembled physical body. We have the metal, the joints, the mechanical constraints. But if we turn it on right now, it is entirely paralyzed.
It's just a dead statue.
It has no idea what position its own joints are in.
Right. We must install a nervous system. Which brings us to Module 2.
The sensors, the actuators, and the control theory required to fuse them.
The syllabus divides sensors into touch, force, proximity, and vision. But the crucial engineering paradigm to remember here is the split between internal and external sensors.
Proprioception versus exteroception.
Exactly.
Proprioception is the ability to know where your own body is in space, even with your eyes closed. Like, you know where your hand is without looking at it.
Right. And in a robot, internal sensors measure the state space of the machine itself, position, velocity, and acceleration of the internal links.
And the most ubiquitous internal sensor is the optical encoder, right?
Oh, by far. Imagine a glass disc attached to the back shaft of a DC motor.
Okay, picturing it.
The disc has thousands of microscopic black lines painted on it. And an LED shines light through the disc into a little photodetector on the other side.
So as the motor spins, those black lines interrupt the light.
Exactly. It generates a stream of electrical pulses. And by counting those discrete pulses, the controller knows precisely how many degrees the motor has turned.
And by using 2 offset sensors, which I think is called quadrature encoding, it can actually determine if the sequence is A then B or B then A.
Yes.
Which tells the robot exactly which direction the wheel is turning. It's brilliant.
So simple, but so effective. And external sensors, conversely, they look outward. They probe the unpredictable environment around the robot.
Like bumper switches for contact, or ultrasonic transducers that calculate the time of flight of high-frequency sound waves just to measure proximity.
Right. But regardless of whether a sensor is internal or external, the KTU model paper guarantees a question on the mathematical characterization of these devices.
Oh, yeah. Course Outcome 2 explicitly demands definitions for dynamic range, linearity, and resolution.
Yes, these are huge.
Let's attack these. I really want to start with dynamic range because people often confuse it with just the absolute physical limits of a sensor.
Yeah, it's not just the max value. Dynamic range is technically the ratio of the maximum input signal to the minimum measurable input signal, and it's often expressed in decibels.
So give me a practical example of that.
Consider an acoustic sensor, like a microphone. The minimum signal is the noise floor, the inherent electrical static in the circuitry itself.
Like a subtle humming.
Right. If a sound is quieter than that noise floor, the sensor cannot distinguish it from static.
It's just lost in the noise.
Exactly. And then the maximum signal is the clipping point, where the sound pressure is so intense, the microphone diaphragm physically bottoms out and the output voltage maxes out.
It just flatlines at the top.
Yeah. The dynamic range is the mathematical span between that noise floor and the clipping ceiling.
So the wider the dynamic range, the more versatile the sensor is.
Precisely.
Next is linearity. I know that a highly linear sensor makes the mathematics of control theory infinitely easier.
It really is a dream for programmers. Linearity describes the maximum deviation of a sensor's calibration curve from a perfectly specified straight line.
So if you graph it, it should just be a straight diagonal line.
Ideally, yes.
Yes.
If you increase the physical stimulus by 10%, the output voltage of the sensor should increase by exactly 10%.
Right.
And that should hold true regardless of whether you are at the very bottom or the very top of the sensor's range.
But the real world is rarely that linear, right?
Rarely. A cheap temperature sensor might output, say, 1 millivolt per degree when the room is cold.
Yeah.
But as the silicon itself heats up and its internal resistance changes, it might suddenly start outputting 1.5 millivolts per degree.
Oh, man, which is a nightmare for the controller.
A total nightmare. If the sensor's nonlinear, you have to implement complex polynomial lookup tables in the software just to figure out what the voltage actually physically means.
Whereas a linear sensor means you can just multiply the voltage by a single, simple constant to get your physical measurement.
Exactly. Much computationally cheaper.
Okay, finally, resolution. This is really about quantization, isn't it?
It is. Resolution is the smallest increment of change in the physical stimulus that can be reliably detected and represented by the sensor's output.
Right.
And it is heavily tied to the analog-to-digital converter, or the ADC. If you have a continuous voltage from a sensor, but your microcontroller only has an 8-bit ADC,
It can only slice that voltage range into 256 discrete steps, because 2 to the power of 8 is 256.
that.
So if a robotic thermometer reads from 0 to 25.6 degrees Celsius, an 8-bit resolution means it can only report temperatures in exactly 0.1 degree increments.
Right. It literally cannot perceive the difference between 20.11 and 20.19 degrees.
It's blind to that tiny change. The physical world is completely continuous, but the digital resolution is basically just stepped.
Great way to visualize it. Master those 3 definitions for the exam dynamic range as the ratio of span, linearity as the consistency of output slope, and resolution as the smallest detectable quantization step. Got it. Now, the syllabus thrusts us into this massive 9-mark showdown on the model paper. It asks us to compare the architecture of CCD and CMOS cameras.
Oh, this is a classic hardware battle.
9 marks means we need to explain the actual solid-state physics of these image sensors.
Right.
So both CCD, which is charge-coupled device, and CMOS, complementary metal oxide semiconductor, they perform the exact same fundamental miracle, the photoelectric effect.
Yeah, photons of light strike a silicon grid, knocking electrons loose and building up an electrical charge in a tiny pixel well.
Right, the battle isn't about catching the light. It is entirely about how we get those electrons out of the pixel and into the processor.
Let's detail the CCD architecture first. In a CCD, the pixels are basically passive buckets of charge.
Okay.
When the exposure is finished, the camera doesn't read the pixels individually. Instead, it uses a precise clocking voltage to shift the entire row of electron buckets down, one line at a time, into a horizontal shift register at the bottom of the chip.
It's a literal bucket brigade.
That is the perfect analogy. Row 1 hands its electrons to row 2, row 2 hands its to row 3, all the way down the line.
Precisely. And once a row reaches that bottom register, the charge is shifted horizontally to a single, highly specialized, extremely low noise amplifier at the corner of the silicon die.
Just one amplifier for the whole chip.
Yes, and because every single pixel goes through that exact same high-quality amplifier, the resulting image is incredibly uniform and pristine.
Which is why CCDs have historically owned the high-end scientific and astrophotography markets, right?
Yeah.
Because of this ultra-low noise floor.
Exactly.
But the drawback of a bucket brigade is that it takes a lot of time to shift millions of pixels through one single toll booth at the corner of the chip.
It is very slow.
And shifting all those analog charges across the silicon requires massive amounts of power.
Right, which brings us to CMOS.
And I used to think CMOS was just like the cheaper and worse version, but the engineering is actually wildly different.
It is fundamentally different. In a CMOS sensor, every single individual pixel has its own microscopic amplifier and analog-to-digital converter built right next to the photodiode.
Oh, wow.
There is no bucket brigade at all. When the exposure ends, every single pixel amplifies and converts its own charge into a digital voltage simultaneously.
So every pixel basically shouts its value at the exact same time.
Yes. which means CMOS is insanely fast.
Yeah.
You can read a CMOS sensor hundreds or even thousands of times a second.
And because the signal is converted to digital immediately at the pixel level, it must require drastically less power to operate.
Exactly. This is why every smartphone and battery-operated drone uses a CMOS sensor.
But there has to be a physics trade-off, right? If
Yeah.
you cram an amplifier next to every single pixel, you are eating up physical real estate on the silicon that could have been used to actually catch light.
That's the fill factor problem, yes.
And furthermore, because you have millions of microscopic amplifiers, they aren't all going to be perfectly identical.
No. Manufacturing isn't perfect.
Yeah.
Amplifier number 4 might run slightly hotter than amplifier number 5.
Which creates, what, fixed pattern noise.
Exactly. A subtle graininess in the image that CCDs just don't suffer from.
So for your 9-mark answer on the exam, you need to structure a really clear comparison. CCD uses centralized amplification via charge shifting, resulting in high fidelity and high dynamic range, but it suffers from low speed and high power consumption.
Perfect.
While CMOS uses distributed pixel-level amplification, resulting in blistering speed, parallel readout, and low power, but traditionally it battles higher noise and lower light sensitivity due to that reduced pixel fill factor.
That'll get you all 9 marks.
Awesome. And the syllabus also includes a specific directive to realize an omnidirectional 360-degree camera.
Yeah, the geometry here is actually straightforward. You can achieve this via catadioptric systems.
Catadioptric.
Yes, which essentially pair a standard camera lens with a convex mirror, typically a parabolic or hyperbolic mirror.
Oh, like those security cameras hanging from ceilings in stores?
Exactly. The camera stares up into the mirror, capturing the entire 360-degree radial field in a single circular image.
And then the software mathematically unwarps that circular image into a flat panorama.
Right. Alternatively, you can use multi-camera arrays, where overlapping fields of view from several outward-facing sensors are just stitched together in real time using feature-matching algorithms.
Okay, so our robot can see and it can feel its joints. Now we need the muscles, the actuators.
Moving right along.
Module 2 lists DC motors, H-bridges, pulse width modulations, stepper motors, servos, hydraulics, and pneumatics.
Let's dig into how a microcontroller actually commands a motor. Because the digital brain outputs logic-level signals, maybe 3.3 volts at just a few milliamps.
Right.
That is absolutely not enough to spin a physical motor that requires, say, 12 volts and 5 amps of current.
It would just fry the chip instantly.
Yes, that is where the H-bridge circuit becomes essential.
I love the H-bridge. It's so clever.
It's a solid-state electronic circuit built with 4 transistors. They are arranged like the vertical bars and crossbar of the letter H, with the motor sitting right in the middle crossbar.
So by selectively turning on diagonally opposed transistors, you control the direction of the massive motor current.
Exactly. Turn on the top left and bottom right switches, current flows left to right through the motor, and it spins clockwise.
And then swap to the top right and bottom left, current flows right to left, and the motor instantly reverses into counterclockwise.
But an H-bridge only controls the direction. It's fully on or fully off.
Right.
To control the velocity of the DC motor, the controller utilizes pulse width modulation, or PWM.
So if you want the motor to run at half speed, you don't magically lower the voltage to 6 volts. You still send the full 12 volts, but you flick the transistor switch on and off thousands of times a second.
Right. The concept here is the duty cycle.
Okay, explain duty cycle.
If the switch is on for 50% of the time and off for 50% of the time during one of those high-frequency cycles, the mechanical inertia of the motor averages out that rapid pulsing.
Oh, because the motor is heavy, it can't start and stop instantly.
Exactly. So it rotates exactly as if it were receiving a constant 6 volts. PWM allows digital microcontrollers to exert highly efficient granular control over massive analog power systems.
That's super cool. Now, while DC motors spin continuously, stepper motors are different beasts entirely, right?
Totally different. They move in discrete magnetic fractions of rotation.
So if the internal electromagnet geometry creates 200 steps per revolution, sending exactly 1 electrical pulse moves the shaft exactly 1.8 degrees.
Yes, steppers offer incredible precision for open-loop control.
Open loop meaning you don't necessarily need an encoder to verify it moved because the magnetic lock is so strong.
Right, you just trust that the pulse moved it. Servos, conversely, represent closed-loop control. A standard robotic servo is essentially a DC motor, a gear reduction train, a potentiometer acting as an internal position sensor, and a little control circuit board, all packed into one plastic housing.
Oh, it has its own brain.
Kind of. You send it a digital target like go to 90 degrees, The internal board checks the potentiometer, sees it is currently at 35 degrees, applies power to the motor, and actively monitors the sensor until it hits 90 degrees and stops.
That's closed loop. It checks its own work. Now, for true heavy industry, we leave electromagnetics behind. Hydraulics use incompressible pressurized fluid, typically oil, to generate terrifying amounts of linear force.
They are messy, they require massive pumps, but they can literally crush cars.
And pneumatics use compressible air. They are fast, they're clean, and cheap. But because air acts like a spring when it's pressurized, pneumatics are incredibly difficult to control for precise intermediate positioning, right?
Very difficult. They usually just slam hard from one end of a cylinder to the other.
Okay, this brings us to what I think is the most critical mathematical concept in Module 2. We have the motors, we have the sensors. How does the code calculate exactly how much power to apply?
This is huge. The KTU exam demands a 5-mark block diagram and explanation of the PID controller.
Proportional integral derivative, the absolute cornerstone of all industrial automation. Let's build an analogy that actually explains the calculus behind this.
Okay, let's do it.
Imagine a drone hovering in the air, trying to hold a perfect altitude of 100 meters. But there is a relentless, steady downdraft of wind pushing it toward the ground.
Right, constant disturbance.
If you only use on-off control, like how a home thermostat works, the drone drops below 100 meters, turns the motors to 100% maximum thrust, rockets way past 100 meters, shuts the motors entirely off, falls back down, and repeats.
It oscillates violently. It is a completely unstable system.
So we implement the proportional term.
Okay, so the controller calculates the error, target altitude minus current altitude.
Right, so if the drone is at 90 meters, the error is 10.
It multiplies that error of 10 by a constant tuning value, called KEP, and applies exactly that much thrust.
And as the drone rises to 95 meters, the error shrinks to 5, so the thrust proportionally shrinks.
It is smooth, much better than on-off. But here is the fatal flaw of a purely proportional controller. Remember the constant downdraft of wind.
Yeah.
As the drone gets closer and closer to 100 meters, the error approaches 0, which means the proportional thrust also approaches 0.
Right, it's backing off the power.
At some point, say exactly 98 meters, the proportional thrust will exactly match the downward force of the wind.
Oh, the forces are in equilibrium.
Yes. The drone just hovers at 98 meters forever. It never reaches the 100-meter target because there isn't enough error left to generate the thrust needed to overcome that wind.
This is called steady-state error.
This is exactly why we require the integral term.
Okay, in calculus, an integral calculates the area under a curve over time.
Right, so the PID controller continuously adds up the accumulated error over time.
So the drone is sitting at 98 meters. The proportional term says, hey, error is only 2, apply a tiny bit of thrust.
But the integral term says, wait, we have been 2 meters short for 10 solid seconds. The accumulated error is growing massively.
The integral term acts like a mathematical spool. It slowly winds up, adding more and more baseline thrust until it finally overpowers the steady-state wind and nudges the drone precisely to 100 meters.
It eliminates the steady-state droop perfectly. But now we have a new problem.
Of course we do.
If the drone is climbing rapidly from, say, 50 meters, the proportional term is pushing really hard, and the integral term is spooling up massively the whole way up.
Right, because it was in a state of error for a long time during the climb.
Exactly. So by the time it actually hits 100 meters, it has so much upward momentum and accumulated integral force that it blasts right past the target, overshooting wildly.
Enter the derivative term.
The
derivative in calculus measures the rate of change, right? The slope of the line. The D term looks at how incredibly fast the error is shrinking. It essentially predicts the future.
It realizes, oh wow, we are approaching the 0 error target at a high velocity. We are going to overshoot.
So what does it do?
The derivative term actually generates a negative output. It acts as an algorithmic brake. It actively fights the proportional and integral terms to dampen the system, slowing the drone down just in time to stop flawlessly at 100 meters without bouncing.
That is amazing. So proportional acts on the present error, integral acts on the past accumulated error to eliminate steady-state droop, and derivative predicts the future rate of change to dampen oscillation.
That is a perfect summary. And for your 5 marks on the exam, you must draw the closed-loop block diagram.
Ray, how do we draw that?
The set point enters a summing junction. It subtracts the sensor feedback to calculate the error. That error signal splits into 3 parallel blocks, P, I, and D. You sum their outputs together and feed that final control signal into the actuator. Masterpiece.
Beautiful. Okay, Which brings us to Section 3 of the blueprint, Sight and Spatial Math. This is Module 3. Our robot's PID controllers can hold its joints totally steady, but its brain is trapped in darkness.
We need to give it eyes.
The syllabus outlines robotic vision, and the model paper dedicates a devastating 14-mark question to this single topic. It asks, outline the 7 stages of robot vision.
If you miss a single step, the logic chain breaks. We need to walk through the actual mathematical transformation of photons into semantic meaning.
Let's do it. Stage 1 is sensing.
Right. Light strikes the CMOS array we discussed earlier. The analog to digital converters sample those voltage levels and generate a two-dimensional spatial matrix of discrete numerical values.
So for a grayscale image, this is just an array of numbers from 0 to 255 representing pixel intensity.
Exactly. The robot does not see an apple. It sees a million-cell spreadsheet of numbers.
Got it. Stage 2 is pre-processing. The raw matrix is contaminated with electrical sensor noise and uneven lighting, right?
Yeah, lots of static. So the processor applies mathematical convolution kernels.
What's a kernel?
It's like sliding a small matrix over the main image matrix, multiplying the overlapping values to calculate a new pixel value. A Gaussian kernel acts as a low-pass filter, basically averaging neighboring pixels to blur out high-frequency digital static.
Alternatively, you might apply edge enhancement filters to sharpen the contrast.
Right. Once the image is mathematically clean, we enter stage 3, segmentation. This is the most computationally fraught step. We must partition the continuous matrix into distinct, non-overlapping regions of interest.
So how does the math actually do that?
The simplest method is thresholding. Say the robot is looking for a bright object on a dark conveyor belt. The algorithm scans the matrix and says, any pixel with a value greater than 150 belongs to the object. Any pixel below 150 belongs to the background.
Suddenly, the continuous grayscale image becomes a simple binary map of ones and zeros. A blob of ones represents the actual object.
Exactly. Stage 4 is description. We have isolated a blob of pixels. Now we must extract topological and geometric properties to describe it mathematically.
So the algorithm calculates the area just by counting the pixels in the blob.
It traces the perimeter. It calculates the center of mass of the shape. It calculates eigenvectors to determine the primary axis of orientation.
So it reduces an irregular blob into a compact mathematical feature vector.
Which feeds directly into stage 5, recognition.
Okay, recognition.
The robot takes this freshly calculated feature vector, say it has an area of 500, a circularity ratio of 0.9, and a red color histogram.
Right.
And it compares it against a pre-trained database of known templates, or passes it into a classifier. The mathematical distance between the current vector and the database vector is minimized.
And the system returns a label. It says, this matrix of pixels has a 98% probability of being an apple.
Yes. Stage 6, interpretation. Recognition assigns a noun, interpretation assigns context and actionable meaning.
How does that look in practice?
The robot evaluates the recognized objects in relation to each other and its current goal state. It calculates the apple is located at pixel coordinates XY, which corresponds to the target delivery zone in my physical workspace. The grasping sequence can be initiated.
It makes a plan based on the label.
Right. Now, the KTU syllabus appends Stage 7, feature extraction. While frequently integrated iteratively between segmentation and description, it is crucial to isolate it for the exam.
What exactly is feature extraction?
It involves identifying highly distinctive, localized data points within the image, such as sharp corners, intersecting lines, or specific localized textures using algorithms like SIFT or SRF.
Why do we need that?
Because these isolated features are robust against changes in scale, rotation, and partial occlusion. It allows the robot to recognize an object even if it is half hidden behind another item.
That's incredibly powerful. So, walk the examiner through that progression, sensing the matrix, pre-processing the noise, segmenting the blob, describing the geometry, recognizing the label, interpreting the context, and extracting robust local features, and those 14 marks are totally yours.
Easily.
But knowing an apple is at pixel coordinate 400, 300, and the camera's 2D field of view is useless unless the robot knows how to translate that into the 3D coordinate frame of its physical gripper.
Which brings us face to face with the apply category again. The linear algebra of spatial transformations.
The math.
It's important. The syllabus demands mastery of pure translation, pure rotation about an axis, and combined transformations relative to rotating frames.
Let's tackle the mathematical dread head-on. The model paper asks, a frame F was rotated about the y-axis 90 degrees, followed by a rotation about the o-axis of 30 degrees, followed by a translation of 5 units along the n-axis, and finally a translation of 4 units along the x-axis. find the total transformation matrix.
It's a mouthful.
It really is. I know we use 4x4 homogeneous transformation matrices to represent this, a 3x3 rotation matrix nested inside alongside a 3x1 translation vector, but how do we string them together?
The absolute most critical concept here is that matrix multiplication is non-commutative.
Non-commutative, meaning A times B does not equal B times A.
Exactly. If you multiply the matrices in the wrong order, you mathematically teleport the robot to completely the wrong location in the universe. The order is determined entirely by the reference frame.
Okay, and the syllabus specifically highlights transformations relative to the rotating frame.
Correct. Imagine the robot's end effector. It has its own local X, Y, and Z axes literally bolted to it.
Okay.
When the problem states a movement is relative to the current local rotating frame, meaning the robot moves forward relative to where it is currently pointing, not relative to the fixed room.
Right.
You mathematically apply the new transformation matrix by post-multiplying it. You multiply it on the right side of the existing equation.
Okay, but why? I really want to push back here. Why does multiplying on the right side suddenly change the physical frame of reference?
It's just beautiful linear algebra. When you multiply a matrix by another matrix on the right, you are taking linear combinations of the columns of the first matrix.
Okay.
And the columns of a transformation matrix mathematically represent the unit basis vectors, the actual pointing directions of the robot's local frame.
Oh.
So by post-multiplying, you are explicitly applying the new movement strictly along the axes of where the robot is currently pointing.
That makes so much sense.
And if you pre-multiply on the left, you are taking combinations of the rows, which applies the movement relative to the fixed global coordinate system of the room.
That is the why that textbooks never seem to explain. Post-multiplication manipulates the local basis vectors. So for the exam question, you construct the 4x4 homogeneous matrix for the 90-degree Y rotation. Then, because the next 30-degree rotation is relative to the new O-axis of the rotated frame, you post-multiply it. Matrix 1 times matrix 2.
Yes. You continue this chain, multiplying sequentially from left to right, exactly in the order the problem states, to build the final total transformation matrix.
Got it. Okay, from the kinematics of stationary arms, we pivot to the kinematics of wheeled robots.
How does a differential drive base or a four-wheeled rover actually navigate through this mathematically defined space?
The syllabus requires us to understand 4 interlocking variables: degree of freedom, maneuverability, steerability, and mobility.
We established earlier that a robot operating on a flat 2D plane has 3 total degrees of freedom in its workspace. It can translate along X, translate along Y, and rotate around Z, which is yaw.
Right. Degree of mobility is the number of those degrees of freedom that can be directly manipulated by instantaneously changing the velocity of the drive wheels.
And degree of steerability is the number of independently controllable steering parameters, like turning the front wheels of a car. And degree of maneuverability is just the sum of mobility and steerability. These definitions lead directly into a highly testable distinction: holonomic versus non-holonomic robots.
I always rely on the shopping cart analogy here.
It's the best one.
A standard shopping cart with fixed back wheels is a non-holonomic system. Why? Because it is subjected to a kinematic constraint. Specifically, it cannot instantaneously translate sideways.
The math behind this constraint involves analyzing the Jacobian matrix of the wheel velocities. For a non-holonomic robot, the rank of the controllable velocity space is actually less than the total degrees of freedom of the workspace.
Meaning, if you want the shopping cart to move directly to the right, you cannot just push it sideways. The friction of the fixed back wheels will fight you.
You must drive forward, apply a steering angle, and basically parallel park your way into that lateral position. The robot must utilize a sequence of forward and rotational movements to achieve a lateral translation.
But a holonomic robot, however, suffers no such kinematic constraints. Its controllable degrees of freedom exactly equal the total degrees of freedom of the workspace.
It is like sitting in a swiveling office chair on a smooth, polished floor.
Yes. You can push off the desk and instantly slide perfectly left-right or diagonally while simultaneously spinning without ever needing to change your forward orientation first.
To physically engineer a holonomic wheeled robot, you must abandon standard tires. The syllabus asks for omnidirectional configurations. The industry standard is the mecanum wheel.
The mecanum wheel, it looks so bizarre.
It does. The rim of a mecanum wheel is populated with a series of passive, free-spinning barrel rollers angled at exactly 45 degrees to the wheel's axis of rotation.
The physics of how these work is fascinating. When you apply torque to the main wheel, the 45-degree rollers touching the ground generate a force vector that points diagonally.
Exactly. So if you mount 4 mecanum wheels on a chassis and drive the wheels on the left side toward each other and the wheels on the right side away from each other.
The forward and backward components of those diagonal force vectors mathematically cancel out to zero.
But the lateral sideways components of the force vectors add together. The entire robot chassis flawlessly slides completely sideways, achieving true holonomic maneuverability.
It looks like magic when you see it, but it's just vector addition.
Just math.
And that wraps Module 3. We've taught the robot to see the apples, calculate the transformation matrices, and slide holonomically across the floor.
But as it slides into Section 4, it encounters a profound existential crisis. Module 4.
The robot stops and realizes, I know how to move, but I have no idea where I actually am.
We are crossing the threshold into localization and mapping. Let's isolate localization first. The robot sends a digital command. Rotate the wheels enough to drive 1 meter straight forward.
Okay.
The internal optical encoders count the pulses and confirm. The wheels rotated the exact mathematical equivalent of 1 meter. Did the robot move 1 meter?
Almost certainly not.
This is the crisis of odometry, estimating position by integrating the rotation of the wheels over time. The syllabus demands an understanding of the error model for odometric position estimation.
And these errors accumulate relentlessly. They are divided into 2 categories, systematic and non-systematic.
Let's do systematic first. These are deterministic flaws built into the physical hardware. The math assumes the wheelbase is exactly 500 millimeters wide. But because of the thermal expansion in the metal chassis, it's actually 501 millimeters.
Or the math assumes the wheels are identical, but the left tire is slightly more inflated, making its diameter like 0.5% larger.
That 0.5% sounds trivial, but odometry integrates over time. It is compounding sum.
So if the left wheel travels 1.005 meters for every 1.00 meter the right wheel travels, the robot's physical trajectory will slowly bend into a massive circle.
Yet, because the internal sensors report equal rotations, the robot's internal map will show a perfectly straight line. The covariance of the error, the mathematical region of uncertainty, grows into a massive ellipse the further the robot drives.
That is just the systematic error. Non-systematic errors are unpredictable stochastics from the environment.
The robot drives over a slick patch of oil, the wheels spin for half a second without gripping the floor.
The optical encoders report forward movement, but the physical robot stayed completely still. Or the robot drives over a thick power cable, lifting a wheel off the ground briefly.
Odometry is fundamentally doomed to drift over time. To solve this, we must fuse the flawed internal odometry with external sensor data. We must give the robot a map and let it look for landmarks to correct its internal estimate.
The syllabus requires probabilistic map-based localization using the Kalman method. This is a monumental algorithm in robotics.
The Kalman filter is an iterative mathematical framework that estimates the true state of a system by combining a sequence of noisy, inaccurate measurements. It operates on a continuous, infinitely repeating cycle of 2 phases: predict and update.
Let's walk through the math conceptually using Gaussian probability distributions, the classic bell curve.
In the predict phase, the robot relies entirely on its odometry and kinematics. It says, I was at coordinate X. I commanded my wheels to drive 10 centimeters. Therefore, I predict my new position is X plus 10.
But because of systematic and non-systematic errors, it doesn't just plot a single point.
No, it calculates a Gaussian bell curve of probability. The peak of the curve is at X plus 10, but the curve is wide and blurry, representing high uncertainty.
It's saying I'm most likely at X plus 10, but I could reasonably be anywhere from X plus 8 to X plus 12.
Then comes the update phase. The robot fires its external laser scanner. The scanner detects a known wall and reports, based on the time of flight of a laser, we are exactly 3 meters from the wall.
But sensors have noise too, so this reading is also a Gaussian bell curve.
Now the magic happens. The Kalman filter takes the wide, blurry bell curve of the internal odometry prediction and the separate bell curve of the external sensor measurement, and it mathematically multiplies the 2 probability density functions together.
And when you multiply 2 Gaussian distributions, the resulting product is a new Gaussian distribution.
But crucially, this new bell curve is significantly narrower and sharper than either of the original 2. The variance drops by mathematically fusing 2 sources of highly flawed, noisy data. The Kalman filter extracts an incredibly precise, high-confidence estimate of the true hidden position. It corrects the odometry drift in real time.
It is mathematical elegance at its finest, fusing internal flaws with external flaws to actually find the truth. But there's a catastrophic dependency built into this entire localization theory, isn't there?
Oh yes, the Kalman filter and Markov localization techniques absolutely require the robot to already possess an accurate map of the environment to compare its sensor readings against.
Which triggers the most famous acronym in all of robotics, SLAM, simultaneous localization and mapping.
The big one.
I want to challenge this because on the surface it sounds like a solved problem. Why can't the robot just turn on its laser scanner, look at the room, draw a map in its memory, and then use that map to localize?
Because you are ignoring the odometry drift we just established. It is a profound, vicious circle. To build an accurate map of an unknown environment, the robot needs to know its exact physical coordinates to correctly plot the location of the walls it sees. But to know its exact physical coordinates and correct its odometry drift, it needs an accurate map to compare its sensor readings against.
The chicken and the egg.
Exactly.
If it relies on odometry to draw the map, and the odometry drifts, it might drive down a hallway, turn around, drive back, and its internal coordinate frame will be off by a meter.
Right.
So when it sees the original wall again, it will draw a second wall right next to the first one on its internal map. The map becomes a completely distorted, useless nightmare.
That is the SLAM paradox. The mathematical definition of SLAM is the attempt to solve a joint probability distribution problem. The algorithm is attempting to estimate the posterior probability of the robot's trajectory and the map of the environment simultaneously, given only the history of noisy control inputs and noisy sensor readings.
The syllabus requires us to differentiate between several mathematical approaches to this paradox. The KTU model paper explicitly poses an 8-mark question. Compare graph-based SLAM and particle filter SLAM.
Let's evaluate particle filter SLAM first, which is frequently implemented as fast SLAM. This approach utilizes a Monte Carlo localization framework.
Okay, Monte Carlo.
Instead of trying to maintain one single complex mathematical equation of where the robot is, the processor generates thousands of discrete particles.
Every single particle basically represents a distinct hypothesis, a wild guess.
Yes, I am at coordinate x facing north. I am at coordinate y facing south. Thousands of independent parallel universes.
And as the robot's wheels turn, the algorithm applies the odometry data to all the particles. Every particle moves forward in its own hypothetical map. Because of the simulated noise, the particles begin to spread out like a cloud.
But wait, if particle SLAM requires throwing out thousands of hypothetical universes and calculating independent maps for all of them every fraction of a second, wouldn't that completely fry the onboard processor of a small drone?
How is this actually computationally practical?
That is the brilliant optimization of fast SLAM. It uses Rao-Blackwellization.
Say that again?
Rao-Blackwellization.
Yeah.
It mathematically separates the robot's path estimation from the map estimation. The processor only maintains the particles for the robot's trajectory. Each particle then maintains a relatively simple, deterministic map of the landmarks based on that specific path.
And when the robot takes a sensor reading, the survival of the fittest begins.
Exactly. The robot's laser scanner sees a corner at a specific angle. The algorithm loops through all thousands of particles and asks, if you were truly at your hypothetical location, what should your laser scanner see?
Oh, I see.
The particles whose hypothetical view matches the real sensor data are assigned a high mathematical weight. The particles whose hypothetical views conflict with the sensor data are assigned a low weight.
In the resampling phase, the low-weight particles are brutally deleted and the high-weight particles are duplicated. Over time, the cloud of thousands of scattered guesses coalesces into a dense, highly accurate point representing the true location and the true map.
Now, contrast that Monte Carlo approach with graph-based SLAM. Graph SLAM abandons particles entirely.
It utilizes the structure of graph theory, right?
Right. The map is built as a network of nodes and edges.
Yeah.
Every time the robot stops and takes a sensor reading, it drops a node into the mathematical graph, representing a pose.
And as it drives to the next location, it connects the new node to the old node with an edge. The edge mathematically represents the spatial transformation, the odometry calculation between the two poses.
It's building a giant web of springs.
A web of springs is the perfect physical analogy. Because odometry drifts, these edges, the springs have tension, they contain accumulated error.
The breakthrough in graph SLAM occurs during loop closure.
What's loop closure?
The robot drives around a large building and finally recognizes a visual landmark it saw at the very beginning of its journey.
It says, wait, I know this corner. I am back at node 1. So it draws a new edge directly connecting its current node, let's say node 100, back to node 1.
But because of the accumulated drift over the journey, the physical coordinates of node 100 and node 1 in the computer's memory do not actually align.
The graph is stressed. The loop doesn't perfectly close mathematically.
This is where the optimization engine takes over. Using algorithms like Levenberg-Marquardt least squares optimization, the software mathematically relaxes the entire graph simultaneously.
It shifts every single node in the web, balancing the tension across all the edges, distributing the error backward through time to find the maximum likelihood map of the entire environment.
So for the 8-mark comparison, Particle SLAM uses a Monte Carlo distribution of weighted trajectory hypotheses and runs efficiently in real time by resampling the most probable states. Graph-based SLAM builds a historical topological network of poses and spatial constraints, solving for the map by running a massive mathematical optimization to minimize the error across the entire graph upon loop closure.
Incredible. We have conquered the existential crisis. We have a map. We know our coordinates within the map.
Which brings us to the final act, Section 5, the master plan. Module 5 of the syllabus. How do I get there? We need path planning and navigation algorithms.
The syllabus hits us with graph search algorithms, breadth-first search, depth-first search, Dijkstra's algorithm, A-star, and D-star.
The KTU model paper makes it very clear how they will test this. They don't want definitions. They present an 8-mark apply question.
They provide a grid diagram with a start square, a goal square, and solid black obstacle squares, and command you to trace the robot's path using the A-star algorithm.
To execute A-star on an exam grid, you must understand how it mathematically improves upon Dijkstra's algorithm.
Right, because if you deploy Dijkstra's algorithm on that grid, it expands uniformly in all directions. It calculates the exact cost from the start node to every single adjacent node, and then every node adjacent to those expanding outward like a concentric ripple in a pond until the edge of the ripple finally touches the goal.
Dijkstra guarantees finding the absolute shortest mathematical path. But exploring every single dead-end corridor pointing in the opposite direction of the goal is a massive waste of computational processing cycles.
Which is exactly why A-star introduces the concept of a heuristic.
A heuristic is an educated mathematical guess. In A-star, the total cost of moving to a specific square, denoted as f, is calculated as f equals g plus h.
The g value is the known absolute cost to travel from the starting point to the current square. That is the Dijkstra part. But what is the h value?
The h value is the heuristic, the estimated cost to travel from the current square straight to the ultimate goal. In a grid environment, this is often calculated using Euclidean distance, which is a straight geometric line, or Manhattan distance, which is counting strictly horizontal and vertical grid steps.
So A-star essentially gives the algorithm a compass. It actively pulls the search space toward the target.
Yes. When it looks at the adjacent squares, it prioritizes expanding the squares that physically bring it close to the goal coordinates, drastically reducing the number of nodes it has to calculate.
So for your 8 marks on the exam, you must physically write out the f, g, and h values in the blank squares surrounding the start point. Always expand the square with the lowest total f value next.
Trace that chain of lowest f values around the black obstacles to the goal.
And there's a crucial exam note here, right? For A-star to guarantee the mathematically shortest path, your heuristic h must be admissible.
Absolutely. Meaning it must never overestimate the actual cost to reach the goal. A straight line Euclidean distance is always admissible because a straight line is the shortest possible physical distance.
Okay, so the robot calculates its optimal A-star path. It begins driving. But path planning assumes a completely static universe. What happens when a human being suddenly steps in front of the robot?
We shift from global path planning to local obstacle avoidance. The syllabus categorizes these as reactive navigation algorithms, the bug algorithm, vector field histograms, and dynamic window approaches.
The bug algorithms sound almost too simple to be true.
They are very basic. Imagine the robot is blind, walking in a straight line toward the goal coordinates, and it bumps into an unexpected wall. Bug 1 behavior dictates that the robot must turn and physically trace the entire unbroken perimeter of the obstacle until it returns to the point where it first hit it.
It traces the whole thing.
Yes, it remembers the single coordinate point along that entire perimeter that was mathematically closest to the goal, drives back around the obstacle to that specific point, leaves the wall, and resumes walking straight to the goal.
It guarantees you will get around the obstacle if a path exists, but it is brutally inefficient. Tracing an entire factory floor layout just to walk around a pillar is absurd.
Bug 2 optimizes this. The robot hits the wall and traces the perimeter. but it continuously calculates the imaginary straight line running from its starting point to the goal.
Ah.
The instant the robot's perimeter tracing path crosses that imaginary straight line again, closer to the goal than where it started, it immediately detaches from the wall and resumes its journey.
Bug algorithms require very little processing power, but modern mobile robots use the dynamic window approach, or DWA. The model paper asks to compare local and global DWA for 7 marks. We need to explain the physics of the window.
DWA shifts the obstacle avoidance problem from physical Cartesian space into the robot's velocity state space.
Explain that.
It maps out all possible combinations of translational velocity, forward speed, and rotational velocity steering angle the robot is currently capable of executing in the next fraction of a second, given its current momentum and the physical acceleration limits of its motors.
So this limited subset of reachable velocities is the dynamic window.
Yes. It's asking, given how fast I am currently moving and how heavy my payload is, what are the steering and braking commands that won't cause me to flip over or skid?
Exactly. The algorithm then projects those safe velocities forward to see if they intersect with any laser scanner readings of obstacles.
It mathematically scores the safe trajectories, heavily penalizing velocities that result in collisions, and rewarding velocities that point toward the goal and maintain high speed. It continuously selects the highest scoring velocity command.
But the exam specifically asks for the difference between local and global dynamic window approaches.
A purely local DWA only looks at the immediate sensor data and the immediate target heading. It is greedy.
What happens if it gets stuck?
Well, if you place a U-shaped desk in front of the robot, the local DWA will see open space inside the U, drive straight into the cul-de-sac because it aligns with the target heading, and then get permanently trapped in a local minimum. It just endlessly spins in place because every safe velocity window points away from the goal.
It lacks situational awareness.
Therefore, the global DWA incorporates a navigational function derived from the larger map, like integrating the A-star path we calculated earlier into the scoring function.
So the global DWA evaluates the immediate safe velocity window against the global path to the exit of the room, preventing the robot from driving into the local U-shaped trap in the first place.
Exactly.
Now, there is a very specific, deeply technical question hiding in Course Outcome 5 regarding vision-based navigation. It asks, in the floor finder algorithm, what does the Gaussian blur function do to improve the results?
The floor finder algorithm attempts to segment the navigable ground plane from the walls and obstacles using raw camera imagery. But a raw image is chaotic. The floor might have a speckled tile pattern. A window might cast a stark, geometrically sharp shadow across the hallway.
If the algorithm is looking for edges to identify walls, a sharp black shadow looks mathematically identical to a physical drop-off or a solid barrier. It will literally paralyze the robot.
This is where the physics of social frequencies comes in. Sharp edges and speckles are high-frequency data. A Gaussian blur is a mathematical convolution that acts as a low-pass spatial filter.
By heavily blurring the image matrix, the algorithm completely destroys the high-frequency data. The sharp shadows soften into gradients. The tile speckles vanish into a uniform average color.
The Gaussian blur function mathematically smooths out the deceptive, high-frequency visual noise, leaving behind only the low-frequency structural blobs of the environment,
allowing the algorithm to confidently isolate the large, continuous, unbroken plane of the floor for navigation.
Flawless explanation. To manage all these complex algorithms concurrently, the syllabus discusses navigation architectures. Software engineering for robotics relies heavily on modularity and controlled decomposition.
You do not write a single monolithic million-line script. You build independent encapsulated modules, a vision node, a kinematics node, an obstacle avoidance node.
This allows code reuse. You can take the highly refined SLAM module you wrote for a wheeled rover and drop it directly into the codebase for an aerial drone, only changing the kinematic translation layer.
And control decomposition defines how these layers interact. A typical hybrid architecture separates the system temporally. The lowest level handles high-frequency, microsecond hardware loops, maintaining the PID control of the wheel motors.
The middle level handles reactive behaviors at millisecond speeds, firing the DWA to dodge a human.
The highest level handles the slow, deliberate cognitive planning, calculating the A-star path to the kitchen over the span of several seconds.
Which brings us to the final frontier of the syllabus. Everything we have discussed so far, A-star, Dijkstra, PID, bug algorithms, SLAM, these are classical, explicit, human-engineered mathematical rules.
But the final topic introduces the alternative, neural networks and convolutional neural networks, or CNNs.
The syllabus asks you to illustrate the incorporation of neural network approaches in robot navigation. Classical robotics is brittle. If the environment changes in a way the human programmer didn't explicitly write an equation for, the robot fails.
Neural networks represent a complete paradigm shift from explicit programming to implicit machine learning.
Instead of writing a rule for every shadow and obstacle, you build a multi-layered neural architecture. You feed the convolutional neural network raw matrices of pixels from the cameras, and you pair those images with the correct steering and throttle commands recorded by an expert human driver.
Through the mathematics of backpropagation and gradient descent, the CNN iteratively adjusts millions of internal weights across its hidden layers.
Over hundreds of thousands of training epochs, the network automatically discovers its own internal representation of the world. It learns to extract the necessary features like lane lines, obstacle depth, and drivable space without a human ever writing a segmentation threshold or a Gaussian blur equation.
It directly maps high-dimensional pixel inputs to low-dimensional steering outputs. It learns to drive through experience and pattern recognition, handling messy, unpredictable, real-world noise with a robustness that rigid classical algorithms simply cannot match.
And that profound shift from classical logic to learned behavior encapsulates the entirety of the AIT 304 syllabus. We have built the mechanical body, wired the proprioceptive sensors, mathematically transformed the coordinate spaces, solved the slam paradox, and navigated the grid.
Now we must synthesize this into a strategy for the 100 marks awaiting you in the exam hall. Section 6, the ultimate exam hacks. Let's break down the paper structure.
Part A consists of 10 compulsory questions worth 3 marks each. Precision is your weapon here. Do not write paragraphs. Hit the mathematical definitions.
When asked about holonomic mobility, explain the lack of kinematic constraints and reference the Jacobian ring. When asked about degrees of freedom, specify the independent variables of the SE3 spatial group.
Part B is the proving ground. 2 full questions from each module. You must choose one. Each carries 14 marks, usually bifurcated into applied subsections.
This is where the Bloom's apply category is explicitly tested. And to prove you are ready, we are going to dismantle the specific physics math problem from the KTU model paper right now.
Question 12b. Assume an object of mass, 140 kilograms, is to be lifted up with an acceleration of 10 meters per second squared. Calculate the gripper force required for the operation. If the coefficient of friction between contact surfaces is 0.2, number of fingers in gripper is 2, and acceleration due to gravity is 9.8 meters per second squared. 5 marks.
Do not let the terminology intimidate you. Break it down into classical Newtonian physics. First, calculate the absolute forces acting against the robot. The payload is not static. The robot is actively accelerating 140 kilogram mass upwards.
So we apply Newton's second law, force equals mass times acceleration. But the critical insight is that there are 2 accelerations fighting the lift. The kinetic acceleration of the robot arm moving upwards, and the constant downward acceleration of Earth's gravity.
Exactly. The total effective acceleration acting on the mass is the upward acceleration, A, plus the gravitational constant, G. Therefore, the total force, F total, attempting to rip the object out of the gripper equals mass multiplied by the sum of O plus G.
Mass is 140 kilograms. Acceleration A is 10 meters per second squared. Gravity G is 9.8 meters per second squared.
F total equals 140 times the sum of 10 plus 9.8.
F total equals 140 times 19.8.
Calculating that out, 140 times 19.8 equals 2,772 newtons. That is the sheer downward force the payload is exerting.
Now, step 2. The mechanical fingers must grip the object tight enough to generate a frictional force that exactly equals and counteracts that 2,772 newtons. We use the standard friction equation.
Frictional force equals the coefficient of friction, mu, multiplied by the normal gripping force, F grip, exerted by the fingers multiplied by the number of fingers, N.
We know the required frictional force must match the total downward force of 2,772 newtons. So 2,772 equals mu times F grip times N.
We plug in the provided values. Mu is 0.2, the number of fingers N is 2.
2,772 equals 0.2 times F grip times 2.
2,772 equals 0.4 times F grip.
Finally, using basic algebra, we isolate the unknown variable F grip by dividing the total force by the constant 2,000.4.
2,772 divided by 0.4 equals 6,930.
6,930 newtons. Write out the formulas. Display the variable substitution clearly. Ensure your final answer is boxed with the correct unit of newtons, and you have mathematically secured 5 marks. The applied category simply requires you to map the physical scenario to the underlying kinematics and physics.
Let's run a final cognitive sweep of the blueprint. When you sit down in that exam hall, you don't need to panic at the sight of the acronyms. You simply close your eyes and visualize the evolution of the machine we just built.
You see the rigid links and revolute joints? You define the 6 degrees of freedom in SE3 space?
You wire the internal optical encoders. You evaluate the dynamic range and quantization resolution of the sensors. You tune the PID controller, visualizing the integral term winding up to fight the steady-state wind.
You calculate the transformation matrices, remembering to post-multiply when operating in the local rotating frame. You identify the 45-degree force vectors of the mecanum wheels.
You watch the systematic odometry errors cause the covariance ellipse to drift, and you trigger the Kalman filter to fuse the noisy Gaussian distributions into a pristine location estimate. You deploy the fast slam particles.
You trace the F equals G plus H heuristic of the A-star algorithm across the grid. You blur the camera feed to extract the floor plane, and you hand the ultimate control over to a convolutional neural network.
The exam is testing a logical sequential hierarchy of systems. If you understand how a mechanical joint relies on an encoder, which relies on a PID loop, which receives commands from an A-star path planner running on a graph slam map, the isolated questions on the paper will instantly snap into their correct context. You have transcended rote memorization. You understand the engineering reality.
You now possess the comprehensive mathematical framework, the physical analogies, and the strategic blueprint to become a robotics god in that exam hall. You are completely ready to dominate AIT 304.
But as you finalize your preparation, I want you to look past the KTU exam paper. We just spent an hour dissecting the beautiful, complex, human-engineered logic of classical robotics, transformation matrices, Levenberg-Marquardt optimizations, heuristic algorithms.
But the very final topic on your syllabus, neural networks, is an omen. The classical foundation you are mastering today is slowly being eclipsed by deep reinforcement learning and end-to-end AI models that discover their own implicit rules.
You are not just learning a syllabus to pass an exam, you are mastering the historical mathematical bedrock of automation.
When you walk out of that exam hall, your real mission begins, taking this classical foundation and being the engineer who pushes the boundaries toward true artificial general intelligence.
Keep analyzing, keep innovating, and good luck on that exam.